So I'll just want to make sure that we can get everything zeroed out first. So I'm going to set a 0 point for both sensors. Okay, now once the angle's down to 0, we don't really care about the potential here. Collect, see it going, bring it to 0.4, let it go. Okay. All right, and now we're going to. Oh, that's okay. Yeah, just stay close. There we go. So now we're going to need to figure out what is the change in potential energy as we go through one swing. So in order to do that, we're going to need to bring in a new calculated column. We're going to call this column potential energy. For short, we're going to call it U, because that's what we refer to it as in the lab write-up. The units here are going to be joules, and now we can write in an expression. So the expression here is found in the lab write-up on the first page, where we have U, gravitational potential energy, equals mgh, but we're dealing with a pendulum here, so we can't just talk about h. We have the change in the position of the center of mass. So that's going to be mg times L, which is the length from the pivot point to the center of mass, times 1 minus cosine of the angle we're sweeping through.
H is changing.
Yes. So to write that out, we're going to have m times g times L times 1 minus functions, trigonometric, cosine, and cosine of the angle. And make sure we don't have a syntax error. Now we can go into parameters, and we're going to make sure that we're dealing with what we need to. So the mass was 91 grams, which is 0.091 kilograms. The length that we have from the pivot point to the center of mass was 8.5 centimeters, or 0.085 meters. G is 9.81, and so we are set. So hit done. Okay. There we go. So
Insert graph.
Insert graph. And so here's what we have for potential energy versus time. So this is us bringing the pendulum up to 0.4 radians. Then we let it go, and it starts going through some swings. So if we want to know the change in potential energy, we can do this. So we're going to start at the top right before we get it swinging. Potential energy is 0.0060824 joules. Okay? And then we let it swing, then we come to our second peak when it's gone through. And potential energy is 0.0050751 joules. So the change in potential energy is going to be the difference between the number we had here, this 0.0060 and stuff, to the number we had here.
That's the energy loss.
Energy loss due to friction in this case. So now we're going to figure out what is the total change in potential energy, not just due to friction, but due to friction plus conversion into electrical energy. In order to do that, we're going to need to plug this load resistor in. So I'm going to take it out real quick, and then make sure we're making electrical contact into both of these inputs. So I'll plug in like this, and that should complete the circuit here. So now there's going to be current going through this load resistor as we have the EMF induced in the pendulum as it goes back and forth.
And it will measure the voltage across the
load resistor.
Mm-hmm. Previously, we didn't measure anything.
Right. So in the run we took before, this wasn't connected to anything, so the voltage was meaningless. This was essentially just noise coming from the sensor. But now we've actually got a measurement we're going to take. So we've got both plugs of the load resistor into the wand, completing the circuit. And so now we're going to do steps 5 through 10 that we just did, which means we're going to pull this back to
the
0.4.
same
So
angle,
we're going to
yes.
make sure that this is at the same angle we used before. We're going to let it go for one cycle. So I will go to collect just like I did before. When I hit this, I'm going to bring this back to 0.4 radians.
Just wait,
Let it go.
zero angle.
Okay. So we need to zero this first.
No, you don't need. Just click and then once it starts reading, then move that. Yes.
So now I'm bringing this back.
To point
We're going
4.
to 0.4, and then I can let it go and stop. So now we can do the exact same analysis that we did before. So now we'll need to update the formula that we use for potential energy to account for the new values of the parameters that we have. So I'm going to edit parameters. The mass is going to be this number, 0.079 plus 12 grams. So that is 0.091 kilograms. L, instead of being 10.5 centimeters, is 8.5 centimeters. So that's going to be 0.085 meters. Gravity stays the same. We don't need to worry about that. We can hit OK, and done. So that's just going to change this graph slightly from what it looked like before we updated things. Okay, so here's our potential energy versus time graph. And now this is the total potential energy. So this is not only mechanical energy lost due to friction, but also electrical energy that's dissipated in the load resistor. And so we can look at
So the difference
is going to be the number 4, which is going to be, if you want more sig figs than that, 0.00600042 joules, basically 0.006 joules. That drops down to right at this other peak. We've got, there we go. Well, it just goes to 0, but 0.0004575 joules. So now we've got a much more significant
difference is.
So the difference is going to be the number we had up here.
Change in potential.
Yeah, the change in potential energy is going to be. So take the difference of those two. That will be the change in potential energy.
Now energy converts.
So now we're going to start from the power dissipation. Okay. So now we can make one more calculated column in order to figure out what power is dissipated to get final energy conversion. So we will need to, once again, make a new calculated column. The name of this column is going to be power. The short name, we're just going to call it P. And the units for power are watts. Oops. Okay. Now the formula that we are going to use is this formula 6 here. So P is equal to, from IE, we can sub in, and we end up getting V over R squared times R plus R. So if we start to type that in, we get V over, well, we need to actually, so that V is going to be variable, so we're going to call it potential divided by R. For the operator, okay, it is the caret. So squared times, and now I'm going to have big R plus little r. Now I can go to the parameters. So I'm going to need to add a couple more. I don't need to do that. Big R is going to be, we had 4.9. That is in ohms. And we'll also add little r. Little r was 3.7?
3.6.
3.6. 0.6. Once again, that's ohms. Excuse me. And so that's gonna, sorry, that's gonna be our expression here. So now we're all set, and we can
Insert a graph.
insert a new graph. So this is going to be power versus time.
Yeah.
So we can, so we can zoom on just the part we're interested in, which is going to be the part where we start to see that big change in potential energy that we want to see. So now I will zoom. Oops, I zoomed too far. 1 times 2. Yeah, I didn't
from
highlight
top to
enough.
bottom.
Yeah. All the way up. There we go. Okay. There we go. So now we want to essentially find the area underneath this curve.
There are 2 peaks.
Right, and so we need the area underneath just the,
Both.
we need both peaks, okay. So the way we're going to do that is from a technique in calculus called integration. If you don't have any background in calculus, don't worry about it. All we really want is the area under the curve. Because this is watts and this is time in seconds, so when we multiply watts by seconds, we get joules. Joules are units for energy, and that's what we want in the end. So, just want to make sure I'm going to do this. This last page. Okay, so we hit analyze.
Highlight.
Right, thank you. I'm going to highlight these two.
But highlight
All the
from
way.
top.
Okay, and then we're going to go to analyze, integral. So that gives us the integral for power is going to be 0.004824 watt seconds. The watts times seconds is joules, which means this is 0.004824 joules. So that's going to be the...
This is the energy converted into electrical.
Exactly. This is the part of energy that's converted into electrical energy.
The energy loss due to friction should be close to the change in the mechanical potential energy.
Right. So now your job is to verify that that's actually the case. So if you don't have these numbers from earlier, thankfully you're able to go back through the video, figure out what each of these energy losses ends up being, and then compare the energy loss from the total with each of the 2 parts. They should correspond.
That's the end.
And that's it.